Hello, everyone. Very good morning to all of us. Depending on where you are, good afternoon or good evening. My name is Tijani El-badawy from Advanced Membrane Technology Research Center at the University of Technology, Malaysia. My presentation today is on membrane distillation for beneficial reuse of oilfield produced water, progress and future outlook. This is briefly the presentation outline. So here we have a bit of a background. Produced water is simply the water component that is associated with the production of oil and gas. It accounts for about 70% of production volumes. It's hypersaline with salinities reaching up to 8 times, that of seawater, and its constituents or its chemistry is location specific. So it dependent on the geology or geochemistry of the reservoir in which it is found. So you have salts of different kinds, emulsified oils, surfactants, metals. By the time it's separated from the crude. So here we quickly look at the background of this study and try to make a case for why researchers have piqued interest in membrane distillation as a technology for produced water. So basically, the conventional treatment processes has seen the primary, secondary, and tertiary treatment stages where you could have produced water oil content down to as low as 5 ppm at the end of polishing and stripping, and you are basically left with water that is hypersaline, and what is usually the management practice is either if it's offshore you just dump in the sea or use for injection, or if it's onshore you probably send it to the evaporation pit, or perhaps dispose in the disposal wells. So all of these management options have in recent years been associated with one kind of environmental impact or the other, and efforts to kind of see a holistic treatment of produced water is really of interest currently. So basically, for membrane processes, you have the pressure driven processes, microfiltration, ultrafiltration, nanofiltration, reverse osmosis. So out of these, NF and RO mostly have been studied extensively for desalination of produced water or hypersaline water, as the case may be. But they have their limitations in that for NF, for example, the sizing is only able to take care of multivalent ions of, say, the scaling ions like magnesium, calcium. For RO, and then it allows monovalent ions, which is the predominant in produced water, the sodium chloride to pass through. For RO, it's able to actually reject all the salt ions, but it also has limitations in terms of salinity. So the higher the salinity, the higher the process is affected. So you have the osmotic pressure build up with increase in concentration of the salt as the process goes on. So it has a limit beyond which basically it cannot go, usually around 70 to 80,000 ppm of salt. So hybrids have also been studied, but one way or the other, either fouling or the individual limitations of the technology comes to play. So recently, membrane distillation has been put forward as a potential, treatment option for hypersaline feed, basically because it has a high tolerance for feed salinity up to 350,000 ppm, and without affecting the process conditions. So basically, it boils down to the membrane that is going to be used in the process, so which is going to form the later parts of the presentation. So what are some of the environmental issues related to produced water management, the current practices of management of produced water? So quickly here we look at the risk associated with, for example, unlined retention pits, where you could have some leakages that could contaminate the soil. Also, the evaporation ponds. There is also the risk of air pollution. Also, these leaks could also contaminate nearby groundwater sources, which could also affect our drinking water, and also maybe, as you can see on the other image, the drinking source for cattle. There have been incidents where, recorded incidents of cattle death associated with drinking of some of this contaminated water. And also recently, the discourse around, disposal of hypersaline produced water in the sea, and how it affects the temperatures because it's the high salinity makes it more denser, and it moves to the bottom of the ocean, and it affects the ocean currents, as well as the, the precipitation cycle, and all of that. So a lot of issues, a lot of discourse around this, and also for deep well disposal. Also there is the recent um, issues with increased seismic activity related to deep well injections that have been traced to either the injection volumes, or injection pressure, or even the proximity to the basement complexes. All of these issues provide or give us the right incentive to look at technologies that actually holistically could handle the produced water. So what happens in membrane distillation? Basically is distillation process, but with the membrane. So on the left, we can see a simple demonstration of how the process happens. So you have the hot feed, passing on the surface of the membrane, and then you have the permeate on the other side of the membrane. So basically, the vapor that is generated from the hot feed passes through the membrane, and is condensed by the cold permeate that is being circulated. So you have the driving force basically is the vapor pressure gradient from the hot side to the cold side, in which pushes the vapor across the membrane to the other side, which is condensed by the circulating cold water. So basically, that is the principle of the MD. However, the membrane itself determines what kind of feed, what composition can be taken care of, and as we will see later. So, but recently there is a growing interest in, first of all, treatment of oilfield produced water in membrane technology, as you can see from the increase in the publications, um, in the last decade or so, and particularly increase in publications for produced water for produced water treatment in membrane distillation. So a lot of work has been done, a lot of studies have been done, but basically still we have a lot to improve to be able to say we move the technology from lab scale to pilot to the commercial application, as we would see subsequently. So here I try to show quickly the state of the art with MDA membranes regarding treatment of produced water. So basically, this is a summary of the current unique membrane surface architectures that have been still being explored by researchers to see how to effectively treat a typical oil field produced water with salts, SDS, and oil components. So you have quickly, I'd like to kind of categorize the membranes and the materials. So basically, the polymer materials and the ceramic materials. The polymer materials have been favored by researchers due to ease of processability, cheaper to acquire, and compared to the ceramic materials. However, the ceramics have reported, higher flux membranes than the polymer material. And also you have the configuration of the module, hollow fiber or the flat sheet. Hollow fibers have been also like put forward as a better option due to its ability to fit in small spaces, ease of cleaning during clean operations, and basically lack of need of any spacing, for as compared to the flat sheet membrane. However, it also has the disadvantage of ease of breakage, either during the cleaning operations or even preparing the modules. So these are some of the, but by and large, the hollow fibers and polymeric membranes are favored in water and wastewater treatments and membrane distillation, particularly. So the surface architectures, we have the Janus, we have the superhydrophobic and the omniphobic membranes. Here also quickly, the Janus membrane is kind of two-layer membrane where you have one top side is hydrophilic, water-loving, the bottom is hydrophobic, water repellent, and so this surface architecture basically, provides some kind of hydration layer at the top that basically absorbs water and repels the oils and the surfactants in the produced water. So you have a layer that absorbs water, repels oils and the surfactants. However, the hydrophobic layer beneath it does not allow water to go further. So it's just the vapor. So this forms kind of basically a separation layer for for the oils in a hydrophilic oleophobic balance. So that is what happens with the Janus membrane. The superhydrophobic membrane, on the other hand, basically we create the rough surface structure and try to lower the surface energy of the membrane so that they super repellent towards water. So that also helps in treating wastewaters in membrane distillation. So you basically have a membrane surface that allows only water vapor to pass through, rejecting other components in the water. However, it's quite tricky, the superhydrophobic and the omniphobic. The difference between the superhydrophobic and the omniphobic membrane is basically the surface energy. So there is a point, the processes of producing them is basically the same. You create the surface roughness with nanoparticle, and try to lower the surface energy with the fluoroalkyl salines, so just like we see in the middle here. So you create some kind of air pockets that suspends whatever liquid that's on the surface of the membrane, allows only the vapor to pass through. The thin line between the superhydrophobic and omniphobic is basically the interplay of the surface energy. So you have in the omniphobic total rejection of anything liquid, be it oil or water, everything. It rejects SDS, everything. So on the other hand, the superhydrophobic has a level to what is basically water, and you find that the oils kind of attached to the surface of the superhydrophobic membrane. So that is basically the thin line between. However, these surface architectures have their own impact on the eventual membrane performance. So while it repels all the oils and the surfactants and what have you, but most times it reduces the flux. So the surface porosity is reduced, because you've added layers of additives that basically clogs the surface of the pores on the surface of the membrane. So it reduces the water flux eventually. So these are some of the things that need to be addressed, in order to have high performance membranes in MD. So basically, this is the state of the art. So in the classes, there's a range of nanoparticles that are used to create these kind of structures, on the surface of membrane. Organic, inorganic, host of even metal nanoparticles, have been used. So here we quickly also see the alternatives, to standalone treatment. We've seen that the standalone treatment could invariably mean like a lower flux, and also the process of making those surface architectures takes a lot of time, and some of the materials are quite expensive. So researchers have also explored the, either integrating the MD with other technologies, or just simply pre-treating the feed prior to use in the MD, which have also shown significant results. So here I just showed two of some of the main works that have been done. Here on the left-hand side, they used PS, the precipitative softening, lime treatment, and walnut shell filtration prior to MD. This actually gave good results. So the PS decreased the particulates and organic foulants. The walnut shell filtration limited the volatiles, compounds, and diesel range organics. So basically, the MD performed well with high salt rejections and considerably good flux. On the other side, we look at studies from a group that have worked on the Marcellus shell play, produced water. They have used electrocoagulation, forward osmosis prior to MD, which has also shown considerable result. However, all these technologies, all these integration and different approaches, in reality, need to be um, looked at from economic standpoint. Eventually, if we want to say, for example, consider the eventual commercialization of some of these. So we have to look at what it means for the operator. Does it make economic sense to integrate this to that, or because of the location, either the weather, or what is the alternative that could be used? So these questions have driven researchers to also look at. So okay, so we say the MD itself is kind of energy inefficient. So what are the things that can be done to make the MD more energy efficient, which we will see in the next slide. Here we quickly see the competitiveness of MD as a desalination technology in comparison to the other known desal techs. Quickly, the MD stands out for its TDS handling capacity. It's basically the highest TDS handling capacity, though it is also still energy inefficient. And as we can see, it's still disposals are still quite cheaper, than handling in MD. But with the alternative sources of energy, as discussed previously, researchers propose that MD could be quite cheaper in the long run than disposals. Considering the current concerns regarding deep well disposals. So in a bid to make MD have make more economic sense, researchers have also explored the deployment of solar energy as an alternative source of energy for the solar. So also quite a number of studies have explored the coupling of solar sourcing to the MD system, and it has produced remarkable results. Recently, also the photothermal membrane distillations have also taken the stage. Where some of the carbonaceous nanoparticles like graphene, carbon nanotubes, which have photothermal abilities, to provide localized heating on the surface of membrane, so direct solar heating on the surface of membrane, and the basically the MD process takes place. without having to need, PV panels or anything. Yeah, so basically that is for the solar. And also the researchers have also proposed the use of waste heat or geothermal heat from sites, so because of the depth of burial of the reservoir, the conditions is usually of high temperature and pressure. So the heat that comes with the fluid as is being produced could actually be utilized to power the MD to basically directly treat the produced water on site in membrane distillation. However, this requires some location specific designing and others, but that's also recently piqued interest of researchers. Other sources of energy include on-site natural gas production used to power MD or microwave irradiation, which are also currently being explored by researchers. Here we just briefly highlight some of the reuse options for produced water outside of the oil and gas industry. The most obvious, of course, is the irrigation. As studies have shown, the produced water is basically has little or no effect on crop safety and even to an extent soil health. However, this can be viewed in light of basically after taking care of some of the toxic contaminants in the produced water, which MD offers that capability. So if the conditions of cheap energy sources can be accelerated, so these are some of the reuse options that could make economic sense, particularly irrigation, livestock watering, habitat and wildlife watering, and even power generation, on site. So, in a nutshell, what is the future, for this line of research? Basically, most importantly, the reliable and cheap alternative to the energy sourcing for MD is crucial to stepping up the technology, and also design of membranes that are quite robust and without trading the performance abilities of the membrane. And also there is a need to conduct a cost benefit and perhaps techno environmental assessment of systems integrated with MD, to justify the integration, despite the promising results that have been reported with these integrations. And also there is the question around handling the MD brine itself. So after the MD, what happens to the brine? Researchers have looked at crystallization to recover valuable minerals from the brines, and also this also needs to be optimized and perfected. And finally, realistically upscaling the whole MD process to meet real time operation expectations. So these are some of the things that moving forward researchers will look at, considering membrane technology, membrane distillation technology for produced water treatment and hypersaline brines generally, to meet commercial expectations. I think I've come to the end of my presentation. I apologize for taking so much of your time. Thank you very much.